Hello, everyone. Welcome. So we're very happy to have David Zureick-Brown here today, who will tell us about Diophantine geometry and uniformity. And how would you like people to ask questions?
Chat is fine. They can unmute as well. I have a separate monitor with chat open, so I'll probably see anything.
Great.
So
Oh,
either way.
go ahead.
All right. So yeah, thank you for the invitation to speak. I love giving talks like this. One quick thing, I'll drop a link to my website in the chat. The slides are available on the website. So if things are going too fast or you have questions later, you feel free to download those. They're just right at the top of my webpage. So let me full screen. And nope, full screen is here. And good. Okay, yeah, great. So welcome. I do number theory and algebraic geometry. The intersection of those areas is often called Diophantine geometry or sometimes arithmetic geometry. And the goal of the talk, I mean, I obviously want to talk about some of my own theorems and interesting stuff, but really the goal of the talk is to explain what number theory and geometry have to do with each other. I also like visual proofs and so here's a nice visual proof of the Pythagorean theorem. It's also a fun question of how many US presidents had an interest in math. I learned from Jordan Ellenberg's recent book, Shape, that Abraham Lincoln had several sleepless nights around the time of the Civil War where he was trying to square the circle, which is, I didn't know it was impossible at the time. So kind of dryly, the basic problem is to solve Diophantine equations. So Diophantine usually means integers, sometimes rational numbers. Here's three equations or three polynomials, two variables each, and you want to solve them either individually or simultaneously. And sometimes they have solutions, sometimes not. Um, the top one does not because rational numbers are real, and this has no real solutions. The left-hand side is always positive, so it's never zero. The second solution actually has one interesting integer solution, but this comes from the problem of how close can squares and cubes be? So this is 25 and 27, so 5 and 3 are the last uh, squares and cubes that differ by 2. So if you want a number this is like an old riddle, I'm an integer, I'm one more than a square and one less than a cube. Here's a solution, but then finding the other solution of this equation answers that riddle. And then this last equation is especially interesting. It has no solutions. In fact, it has no solutions mod any prime or over, sorry, it has solutions mod every prime and over the real numbers, but it doesn't have any rational solutions. So anyway, this is all to say that solving polynomial equations is hard. Here's the basic problem. V for vanishing or variety. You pick some polynomials and you try to simultaneously solve them. And it's not just a fact that it's difficult, it's provably difficult. So David Hilbert, around the turn of the century, gave what he thought were the 26, I think, most important problems at the time. So of course, the Riemann hypothesis, which is still open, was one of these problems. Oh, actually, that's a great question. So does the second have only one real solution? Once it has one solution, it'll have lots of solutions. So if you move this to the right, there will be lots of small values of x where the right-hand side is positive. Yeah, so it has uncountably many, in fact, but no rational solutions either. So David Hilbert phrased the following problem. He said, devise a procedure by which, so he didn't say prove or disprove. So in our modern language, find an algorithm, write a Python program that takes as input some integer polynomials and output just a simple yes or no as to whether there is a solution at all. And so when Hilbert phrased this, I think they were not as familiar with impossibility proofs or Gödel's incompleteness or any of that. They certainly hadn't seen the halting problem. And it turns out you can, a computer is a collection of code, a program is a collection of text at the base level, and that's a mathematical object that you can prove theorems about. And in fact, you can prove that no computer program you write will solve this problem. So it's amazing. If you're looking for an interesting way to spend a few months, this is something fairly accessible. Oh, the second one. Yeah, the second one only has one integer solution up to squares, but might have more real solutions. Exactly. Um, by the way, this problem, a lot of people say, wait, why isn't brute force an algorithm? So for example, for this first equation, exactly, and chat, it may one day it finds a solution. But if you try 0, 0, 0, 1, 1, 0, if it finds a solution, then you've found it. But maybe it never, maybe there's a solution that you never find. And so certain classes of equations have algorithms. So all of these classes of equations, well, the first one, you can use linear algebra. It's a quadratic form. And so there's a algorithm to solve these. The third one, if you assume $1 million of conjectures, so the Burton-Swinnerton-Dyer conjectures, or at least just finite part of it, finiteness of Shaw, there's an algorithm. But in general, there's no algorithm. For other, rings, the answer may be yes or it may be no. Over the complex numbers, yes. For the real numbers, elimination of quantifiers works. For a finite field, trying everything actually works. And then surprisingly, it's still unknown over the rational numbers. The kind of implication goes the wrong way. If you could solve it over the rationals, you could clear denominators and solve it over Q. So here's the particularly difficult collection of equations to solve. There are some visible solutions involving zeros, and as many people know, or this inspires many people like myself to get into math, that these are the only solutions. And so this took 300 years to prove. It was, you know, uh, initially conjectured, I'll phrase it, by Pierre de Fermat, and then solved later by Andrew Wiles. Also, fun side question. So here's Fermat, here's more number theory, Sophie Germain, here's the lien on a stamp. I was curious of how many mathematicians appear on stamps, and there's a website dedicated to that. So there are 436 distinct mathematicians that appear on stamps. Um, yeah. And then this question from chat, this is great. Could we ever find such an algorithm? Oh, I didn't know that, Simon. Yeah, could we ever find such an algorithm? Yeah, no. There's a proof that there is no algorithm. So it's actually impossible. No algorithm exists. What does the upside down plus sign? Yeah. So this is plus or minus. This one's minus plus. So this just means if this is plus one, this is minus one. If this is minus one, this is plus one. It's just kind of a notational hack to fit things on one line. So in the aftermath, Andrew Wiles proved it. He looks thrilled with himself. Famously, there was a gap in the proof. This is not just a tasteless joke. The Gap Jeans company actually approached Andrew Wiles about doing a jeans commercial, which he was not offended, but he politely declined. He doesn't love being in the spotlight. He was also approached by, not Simon might not even know what 2020 is, but this was a popular interview show at the time. He was even approached by Barbara Walters to do a hour-long primetime interview, declined that as well. Well, now he works in the building with his own name on it at Oxford. And there's a few books. When I was getting into mathematics, first I read Fermat's Enigma, which is a great book about the story of Fermat's last theorem. Although, this book is kind of more focused on mathematicians as people than it is on the mathematics, which is great. Mathematicians are interesting people, but it's somehow easier to write, in my opinion, that type of book. There's an author I really like named Ian Stewart who is very good at writing books that try to explain to a non-mathematical audience what research mathematicians do. And so what led to me learning and studying math and becoming a mathematician is I picked up this second book, Nature's Numbers, which explains, for example, how Fibonacci numbers appear, in nature in spirals and, number of petals on certain flowers or pineapple spikes and rinds. And then I went to the math library and there was a whole shelf of books by Ian Stewart. The most popular one was Does God Play Dice, which is, a famous Einstein quote about chaos theory. But my favorite was this book called From Here to Infinity, which explains, for example, how to uh, how to make a computer out of a train set, a very slow computer. So what a Turing machine is, explains what the monster group is, but to a lay audience. And so I'm a big fan of these. Basically, I read those that summer and switched my major to math. Yeah, an Ulam spiral. One thing I'll say is I went to college in 2000, so it's pre-YouTube. There weren't videos then. These days, there are just so many good YouTube channels, and many of my students study math specifically because of spending so much time learning about accessible things like the prime spirals. And of course, there's a lot of interesting number theory in pop culture, and I'll move on to content after this slide. In The Simpsons, famously, when you used an old calculator, the solar-powered ones, this looked like a solution to Fermat's last theorem. It's just that when you add those together, it overloads the calculator. It's out of the range. That's somehow less offensive than the donut deforming to a sphere one. There's a great number file back to YouTube episode about this. So arithmetic geometry, the basic problem is, again, you have some polynomials, you want to solve them. I mean, there's other, you don't have to look at polynomials. That's another field of math. This is already difficult enough. And I kind of like to break down the type of research or questions people ask into three categories. So one is qualitative, like Hilbert's 10th. Is there even a single solution? Are there infinitely many? Is there some kind of extra structure like group or geometric? Really interesting to me, and I'll show you examples. Quantitative, how many solutions are there? How large is the smallest? Can we find them all? Can we find them all with proof? Those are two different questions. Can we confidently find them all, but without a proof is a very different question than can we prove that we have them all? And then there's kind of a more conceptual or implicit question, like what controls this? Why do some equations have solutions or not? Why do some have many or none? What controls this? And so the first example many people see is Pythagorean triples. So these are solutions to the Fermat equation, but with squares. There are infinitely many. Here's another proof: x squared plus y squared equals z squared on the bottom. These are triples. These are all coprime, meaning no common prime divisor of all three. And there's a nice geometric proof, which is the following. So the equation x squared plus y squared, let me flip back, z squared. If you divide by z squared, you get 1 on the right-hand side. And these are all squares, so you can really, really look at a circle. So there's a trick of turning it from what looks like a surface into something one-dimensional. And then there's a bijection. There's a back and forth procedure. Here's one solution, -1, 0. And, oh, why is it not z? No, it should go this way. The x solution is in the function. Yeah, no, it should be, or unless I misunderstand, it should be this way. These are polynomials. The x's don't solve them. When you plug in x as a variable, it's still non-zero. So I'll put it that way. But yeah, so there's something geometric. Here's one solution. If you have a second solution, x comma y, you can draw a line between your distinguished solution and the hypothetical one, and that will intersect at a point on the y-axis that we'll call 0t. So if you give me x, y, I can produce t for you. And then it's algebra to work out a formula for t in terms of x, y. In fact, it's the slope of the line, so y over x plus 1. And conversely, if I have a point on the y-axis, then drawing the line through the distinguished point and that point gives a unique point on the circle. So if I have t, I can work out the coordinates of x and y. And this lets us parameterize, so t is our parameter, the set of solutions, the rational solutions. And so notice, if x and y are rational numbers, so is t. And conversely, if t is a rational number, so are x and y. And so you can capture this in the following way. I guess I switched to ABC, but kind of clearing the denominators from the previous slide, the solutions to this equation are all multiples of this particular A, B, and C. Another way to put it is there's some geometry to this equation. It's not just a circle, but you can use the fact that it's a circle to find all the rational solutions. This is kind of the first case. Okay. I'd like to spend a lot of time talking about one of the cornerstones of Diophantine arithmetic geometry. So the Mordell conjecture, this is conjectured in the 1920s and proved by Faltings in 1984. This is part of what Faltings, or what it got his Fields Medal for, basically. And so we just saw, I dehomogenized. This equation has infinitely many solutions, and it's a theorem that if we increase this exponent from 2 to something that's at least 5, that then, kind of like Fermat, this fixed equation for this fixed n has only finitely many solutions. For 3 or 4, there's some ambiguity. More generally, and then I'll work up to what the kind of full statement is, the x isn't that important. If you take y squared equals some polynomial, and when you factor that polynomial, there are no repeated roots. So that's what square free means. When you factor it, you get no squares in the factorization. And if that polynomial has degree at least 4, then this fixed particular equation has finitely many solutions. And so the theorem was originally the Mordell conjecture. There's always I don't know if social is the right word, question about when do you stop referring to a proved conjecture by the name of the conjecture versus the name of the person who proved it. In this case, it's about 50-50. People often call it Falting's theorem or the Mordell conjecture. And I think it's the same Mordell, but I'm not sure is that. And mathematicians of that era tended to do lots of different things, not just whatever area they worked in. Um, so why is Fermat believable? Um, if you look at the homogeneous equation, so every monomial has the same degree, it looks like a surface, but you can dehomogenize and get a curve. And what the Mordell conjecture really says is that there's a rather crazy connection between solving equations and geometry. Okay, so here's another conjecture. This is equation, y squared equals a sextic, so degree 6. On the left is Dan Aykroyd from the movie Coneheads, is the graph of the real points of this. So if x is large, the right-hand side will be positive or negative. So the graph is kind of bounded in each direction. And these are the real solutions. And the real solutions are a cross section, so like intersecting with the plane of the complex solutions. So this on the left, which I drew a sage, is a cross section of this on the right, which I drew myself. I'm in math, not graphic design. And you can kind of see that if you were to slice this two-hole torus down down horizontally with the plane, you would get these 3 circles. There's a little subtlety about what the topology, what the picture of the complex solutions look like. But if you have a curve and look over the complex numbers, you get a torus with some number of holes, and you call that number of holes the genus. Mordell's conjecture, more generally, was that a curve of genus at least 2 has only finitely many rational solutions. So Pythagorean triples, that turns out to be genus less than 2. This equation is genus exactly 2, and so his conjecture, proved by Faltings, says that this particular equation has finitely many solutions. Of course, it might have some solutions. If I plug in x equal to 1, this is 0, y equals 0 works. There might be less clear solutions. And this is a crazy conjecture, especially for the 1920s. It's saying that the topology, the complex solutions, and the picture you get somehow is connected to the integer or rational solutions. And so thanks for setting me up. There's a formula, actually, from if you have a smooth plane curve, then the genus is, if n is the degree of the plane equation, the genus will be given by this. So for Fermat's equation, this is a smooth plane curve. Smooth means the thing from multivariable calculus. You take derivatives and have no excess solutions. So this genus is at least 2 if n is at least 4. So what this tells you is that okay, Fermat's last theorem is much harder than this, but for any fixed n greater than or equal to 4, this equation has finitely many solutions. Fermat's much harder. It's saying as you go over all n, there's finitely many, but this is still a pretty interesting intermediate step. One other interesting thing is that Fermat, uh, yeah, so Fermat, and I'll come back to these questions in the chat. These are great. When n is 3, we were just lucky. This is a curve of genus 1 that turns out to be an elliptic curve. If we put coefficients in front, this equation could have infinitely many solutions. And so I backtrack to 2. So there's two things. One is the genus formula requires it to be smooth. This one has some mild singularities. And so the genus formula is a little off. But in general, uh, the intuition for the genus formula is not straightforward. To me, it really comes from some kind of duality involving integration. There's a way to, so on these tori, the number of visible holes is equal to half of the number of loops, independent loops you can draw. And then you can integrate around the loops. And so the intuition for it really comes from, to me, comes from geometry. There's a few ways to prove it using combinatorics as well, or using maps, but the intuition really comes from complex calculus, but not just on the plane, on manifolds. I'm going to talk about some other problems. So an even older problem is the congruent number problem. So you say that a number, yeah, I need more tools to develop it. So really, again, it comes from integration uh, and doing analysis, doing calculus on manifolds. But once you do, it's very transparent. There's a setting where it's a uh, really clear calculation, but there's work to get there. So here's an elementary problem. It's kind of ancient. Say that a number, in this case 6, highlighted red, is congruent if there's a right triangle with integer or maybe rational side lengths and whose area is 6. So 6 is congruent because the 3, 4, 5 right triangle has integer side lengths. That's one equation. And then its area is 6. So 3 times 4 is twice 6. You can capture this as a pair of equations. The first one's homogeneous, and the second one's not. So this is with the Pythagorean theorem for the side lengths, and this one is for the area. So 6 is congruent. You can start with 1, and in ancient times, Gauss and others, or even before Gauss, went through and tried to understand which numbers are congruent and which are not. And it turns out that it conjecturally depends on what this red number is, mod 8. And if you, the first truly interesting case, you'll see why, is 157. So if you assume $1 million worth of conjectures, the Birch-Swinnerton-Dyer conjecture, that will tell you, if it's true, that this pair of equations has infinitely many solutions, not just one or two. But the conjecture, yeah, right. Sometimes you have to assume $2 million worth of conjectures. So Riemann hypothesis. This one, you only need 1 million. And but the neat thing about these conjectures is it doesn't tell you what the solution is. It tells you that there are infinitely many. If you phrase it right, it might answer the next question for you, but you can ask, okay, there we go. So BSD, there's infinitely many solutions, and you can ask how large is the smallest solution? So I'll say the height of a number is roughly the number of digits. So how many digits do you think the smallest solution has? And if I were better at Zoom, I would make a poll. Usually I poll the audience, and 10 seems large. Well, let's just do it. So the smallest solution has 44 digits. I had to factor the denominator of z to fit it on this slide. It's straightforward to take these 3 numbers, plug them in for x, y, and z on a computer, and check that they solve this equation. But this is truly a needle in a haystack. How on earth did anyone find this solution? And then there are more solutions. Okay, so Heegner points is the answer. There's a complicated recipe involving the proof of Fermat's last theorem, not the statement, so modularity, and a lot of complex integrals and stuff where you 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 do a bunch of stuff with complex numbers or real numbers to some precision, but then at the end of the day you get rational solutions. It's really kind of a magnificent thing. And then the next solution has 176 digits. How on earth do you find that? And I really like doing the following back of the envelope calculation. So if you didn't have this roundabout procedure, so my previous institution, Emory University, it was a joint math and computer science department. So I had access to some fast computers. And on Emory's fast computers, if I ran for 1 minute, just plugging in 000, 001, 101, et cetera, I could do about 10 to the 6 in a minute. And then at the time, so it would take this many years, so 252 years, sorry, 10 to the 252 years on one computer. Well, what if you used every computer in the world? In 2011, there were supposedly 10 to the 9 many computers in the world. So that cuts it down to 10 to the 243 years. Of course, the expected time until the heat death of the universe is 10 to the 100 many years, so we would never find it by brute force. Also, this isn't a picture of heat death. Heat death doesn't look like anything. It's a supernova, but needed yeah, great. So there's a lot of interest. I want to show you some other interesting Diophantine problems. This is a surface now instead of a curve. There's a lot of ways to generalize the Fermat conjecture, and I'll show you a few. So a Fermat surface, when you this is 4 variables, so it's dimension 3, but when you homogenize, it's dimension 2 again. And this has more solutions. You can force solutions when there are zeros, but also I can set x equal to z and y equal to w, or x equal to w, y equal to z. Or if n is odd, x equal to minus z, w equal to minus y. But these are one-dimensional, and these formulas are linear, x equals z. So these are lines on the surface. And so the right question to ask is not to show that there's finitely many, but to show that the solutions are codimension 1. If your space is 2-dimensional, you want the set of solutions to be 1-dimensional. So in this case, it's lines. And we've tried nothing, and we're all out of ideas. The ideas from the proof of Fermat's last theorem don't work at all. The geometry of surfaces is much more difficult than curves. Once you get into the geometry, there's like a precise point where Weyl's proof at the very beginning can't even get off the ground. So there's not a single value of n for which anybody can prove the 2 or higher dimensional Fermat conjecture. It's completely open. In contrast, Fermat's last theorem, when we just had x, y's, 3 variables, there was a rich history of mathematicians, even Gauss and Euler, solving particular equation or solving this equation for particular values of n, n equals 3, 4, etc. Here, there's not even even just solving this equation for 5 over the rational numbers would be really interesting. Why is it a surface? So one thing is with one equation and 3 variables, okay, that's 3-dimensional rather than 2. So 4 variables, 1 equation cuts it down to 3. But then this is homogeneous. So we can do the same trick we did with Pythagorean triples where we divide by w. And so really you just get these and then a 1 here. So it's naturally a surface, but you can kind of cheat and cut it down. Sorry, naturally a threefold, but you can cheat and cut it down. I think we're more likely to solve the Riemann hypothesis before we solve this. So it's not true that 2 of x, y, and z are forced to be 0. For example, 1, 1, 1, 1 solves it, or 2, 2, 3, 3. So there are infinitely many here. So even the statement of the conjecture has some extra subtleties to it. So yeah, that's a good point. If one of the, well, actually, that's not even clear. Maybe hypothetically, maybe there are solutions where one of them is 0, but that's a good point. So we want the trivial ones to be Yeah, that's right. By Fermat's theorem, if one of these is zero, you have to have two zeros. That's I like that. That's a good observation. Here's a twist of this. So I've already homogenized, and so notice the cutoff was 5. When n is 2, I'll actually go back. When n is 2, the same trick where you parameterize Pythagorean triples works. It just happens in higher dimension. You can still draw a line and intersect. When n is 3, there's some deep geometry. It's the type of thing you would learn at the last few weeks of a graduate algebraic year-long graduate algebraic geometry course. So when n is 3, there's this. It's a cubic surface. There's 27 lines. It's a really beautiful subject. When n is 4, actually, it's what's called a K3 surface. It's kind of in between very general and very special. And Noam Elkies, when he was 19, realized that that surface had an elliptic curve on it, and that elliptic curve had infinitely many points. But anyway, for 5 or greater, as I'll show you later, there's been extensive efforts to even just, it's important to prove true theorems, so extensive efforts to just look and see with a computer if there are solutions we haven't found, and to make sure we're trying to prove a true theorem. And yeah, nothing out there. But if you twist it a little bit, so instead of the coefficients 1, you have a 2 here and a 4 here. Swinnerton-Dyer studied the surface. It's not actually a picture of it, but it's a pretty picture. And conjectured that the kind of obvious solutions, the ones that jump out at you, are the only ones. So if 1 and 1, 0, 0, I could put a -1 here. Those are the only integer or even rational solutions. And when I was a beginning graduate student in 2004, this was a problem that my PhD advisor, Bjorn Poonen, had as a potential thing for people to work on to prove that these were all of them. And then in 2006, fortunately, right away, before I thought about it much, a pair of computer scientists, so Eisenhower and Janel in Germany, uh, using ideas more from computer science and mathematics, found a way that's a combination of it's like smart brute force uh, to find a solution on this. There's actually nothing fancy about it. They're using the fact that even though there's 3 variables, you can put 2 of them on one side and the other one on the other side. You can actually separate the variables, and made a lot of computer science optimizations to eventually find this 8-digit solution. Unlike the congruent, this is still pretty big, or is it 8 or 7? 7 in the denominator. Um, Problem, find another solution. Now our understanding of what controls whether there are finite or infinitely many solutions has changed. Um, Again, there's some ideas coming from analysis, poles of L functions. And now the conjecture is this has infinitely many. We expect the next solution to have around 40 to 50 digits, so we're not going to find it via brute force. Even finding this by trying 0, 0, 0 with all the computers in the world would take 10 to the 16 years, which is presumably greater than the age of the universe, so which is only roughly 10 to the 10. And these are, yeah, these K3 surfaces have really interesting geometry. And here's one more. Recently in the news, my colleague Drew Sutherland and Andrew Booker solved the following problem. So an ancient problem, you can ask, when is an integer a sum of cubes? So 1, 2, 3, these are sums of cubes. 3 is actually a sum of integer cubes in 2 different ways. 4 and 5 are not. Actually, okay, 9 is a power of 3. If you look mod 9, then there's a condition mod 9 for this to have a solution, and that condition fails mod 4 or 5. So try that yourself. Should 6 be -1? No, 6 is fine. Yeah, yeah. There should be -1s. Very good. Yeah, thank you. Nobody noted that before. Great. So for small values, it's not too hard to do it by hand. This is a conjecture that's still open. We'll probably also solve the Riemann hypothesis before this one. And so the conjecture is when there's not a mod 9 congruence condition, there should be a solution. And people have worked on taking data. So for 32, that's not good mod 9, so there's no solution. And for 33, so Drew Sutherland is an especially interesting mathematician. He got a degree in math and computer science from MIT in the 90s, left for a crypto startup, cashed out, so he had some money, and then went back kind of later in life to get a PhD in math, and is now the best collaborator anyone can have because he actually like learned to program as a programmer, not as a mathematician. And so he's able to do things like they set up a really highly optimized computation to show that the first solution to this equation, sum of three cubes is 33, is this gigantic uh, beast. And it's an interesting mix of math and computation. They also did some other fun ones like 42, great number. Uh, nice shirt down there. Uh, and then there's still they found other solutions for three. Anyway, the kind of theme of this is that even simple inputs, sum of cubes equals 33, uh, might have outrageous first solutions, outrageous outputs. You can kind of ask what the conjecture is when things are very general. So, like for the Fermat setting, when the exponents are at least 5, the geometry becomes very general, and there's some expectation that when things are very general, nothing out of proportion uh, happens. But in these intermediate cases, before things are very general, we expect these kind of sporadic outliers. Um, oh, that's a good question. I'm not actually sure if, so for the other integers question, there are some that have multiple solutions other than three, and I'm not sure. I think the expectation is, yeah, the expectation is there are finitely many integer solutions. So if let me flip back. For fixed n, there should be finitely many integers solving this equation, but there might be more than one in these cases. Um, and then about the emergence of these numbers, I mean, the statement of the problems, I think, are beautiful and interesting, although that's personal taste. The only interesting thing about sometimes large numbers have interesting properties, like the order of the monster group, the prime factors of that uh, suspiciously coincide with other problems. Uh, these numbers don't seem, they seem senseless in some way. Um, Yeah, I think yes, quantum computing will eventually, I don't know when, but will eventually revolutionize these things. People have built physical qubits. If you're interested in that, my friend Christelle Vincent, who's at Vermont, has been giving lots of talks about quantum computing for mathematicians, and it's something we should all start thinking about or getting in on. 114 is the next interesting case. All right, one more. So generalized Fermat equations. So Bjorn Poonen was my advisor. He's famous for a few things. He was a four-time Putnam Fellow. Uh, when I started grad school in 2004, I met him at T. Um, and it's easy to make conversation with mathematicians. You just ask them, what have you been working on or thinking about lately? That's all you have to do. And buckle up. And so I asked him, what has he been working on? And he explained this to me. It's crazy. He looked at this particular generalized Fermat equation. So there's three variables, but now the exponents are not equal. And so got a private message. I'll answer that in a bit. So the exponents are not equal. This is genuinely a surface, not a curve now. There are some solutions that jump out at you. And then there's, the Catalan solution, meaning the 7's not involved in the solution, just x squared plus y cubed equals 1. So if you have 2, 3p, this will be a solution. And then a little bit of computer research found, or even by hand found, this solution when z is 2. You can solve this. But I said there's 16 of these, and at some point in the 90s, computers were slower, and people hadn't realized there were a couple more solutions that have 8 digits. I actually, when students are learning Sage or Magma, I like to give them the statement of this and have them try to find it. 8 digits is hard to find with brute force, but there's a trick. You can cut it down. You plug in for y and z, and then you just check whether z to the 7 minus y cubed. You check whether that's a square. So rather than having to iterate over x, you iterate over y and z and just ask if it's a square. That's faster. But then proving that these are all the solutions, this was published in Duke Math, which is roughly the fourth best journal. It was the first time, it's 51 pages just to solve this one problem. They introduced, I would say, three different new techniques that are now used widely just to solve this problem. So somebody asked privately about descent, so they introduced a new version of descent. Um, Another famous theorem of Bjorn is the big mouth theorem. So this comes up on Reddit and Imager and Instagram all the time. And then there's always a commenter that says, that's not a proof that he has a big mouth. He might just have a small fist, which is actually true. So Bjorn is missing a joint in his thumb on his right hand, which is why he can make a small fist. But here's how he feels about those. So why is 237 so interesting? There's a very general framework for these. So x to the a plus y to the b equals e to the c. And 1995, so after the proof of Fermat's last theorem, Darmon and Granville studied the generalized Fermat equation. And you can't solve it all at once, but you can at least, kind of like the Mordell conjecture that I showed you before, prove that for fixed a, b, and c, such that this weird quantity chi with these denominators is less than or equal to 0. So there's some constraint. So for example, if a, b, and c are each 1, okay, or 2, there's Pythagorean triples, there's infinitely many solutions. So there's some conditions. Then that fixed equation has only finitely many solutions. And I'll just say without elaborating more, even though this is about a surface, there's a weighted action of the multiplicative group, the kind of scaling you do, and there's a certain exotic geometric object called a stack, which is one-dimensional. And really what they did is they reproved Falting's theorem for stacky curves instead of curves. And this chi is the analog of the genus or Euler characteristic. Right. So aside from, I'll save questions about that until later. Um, and so when you look at experimentally solutions of this equation where, okay, this range is good, there are a few. So you can see the 8-digit solutions, 237, 237. There's a couple for 8, like here's one, here's another one. And then experimentally, no one has been able to find any more solutions to this. So similar to Fermat, but there are a few sporadic solutions, a few extra outliers, and then we expect things to stabilize. Somebody asked earlier about, where do these numbers come from? In this case, these numbers actually all come from somewhere. The particular numbers are not that interesting, but they're related to some exotic elliptic curves that exist. So the existence of these solutions happens because of the existence of some other interesting geometric objects. So Andy Beal, who took some math courses, liked math, but he works in finance, is the one who technically conjectured that these are all the solutions. But usually it's attached to a couple mathematician names as well. But Beal, inspired by Clay, well, actually before Clay, he initially put a $50,000 prize for a proof of the conjecture. Later upped it to $100,000, but then to keep pace with Clay and the Clay problems, upped it to $1 million. So I think about this problem all the time. I've had ideas to solve it, but have not solved it. My best friend tried to convince me that it's not a good return on investment to try to solve this. I should just get tenure and make a salary. But there's a prize for the counterexample. It's not $1 million. The prize you get depends on what this quantity chi is. Yeah, and so excellent question. If you go back to whatever this unspecified exotic geometric object is, this chi being less than 0, or strictly less than 1 if I move the 1 over, corresponds to this being hyperbolic in the geometric sense, or being very general in some sense. So this chi being less than 1, that's the analog of genus at least 2 in the Mordell conjecture. So and hyperbolic means negatively curved. I'll put it that way. So a sphere is positively curved. When you draw triangles on it, the angles can add up to more than 180. This condition is somehow the other extreme. Things are negatively curved. Triangles can be add up to less than 180. So there's extensive data. Again, another thing from the 90s that will sound made up to you now is that when your computer was idle and connected to the internet, you could install a program called SETI at home, which would, when you're not using computer, use your, spare computer cycles, whatever you want to call them, to help search for extraterrestrial life. So the ET or intelligence. So it's the search for extraterrestrial intelligence. Eventually, people said, aliens are interesting, but let's use it to do number theory. So there was a similar project where you could donate the spare time on your computer, parallel collaboratively to look for interesting solutions to the ABC equation, but in particular to other solutions to this generalized Fermat equation. And they found interesting solutions, but not any more to this. So maybe instead of this equation, you can solve it, but there's a 7 in front of z to the c. So they found kind of near solutions that were not quite solutions. And there's a lot of data. The data file for this is, yeah, Simon, yeah, exactly right. Mersenne prime searches. The data file for this, for the ABC near misses, is 2/3 of a gig. And when I tried to open this, it crashed my text editor. So I didn't realize you can't just open such a large file. And you have to use, bash or whatever to solve it. So going back to this, there's that number 42 again. What's so interesting about this equation is it's the first interesting case. So if you look at the ratio half, third, seventh minus 1, you get minus 1 over 42. Here's a fun elementary number theory puzzle. If you replace 7 with 6, you get exactly 0. 5 would give you something positive. So minus 1 over 42 is the closest this quantity chi can come to 0 from below. There's a probabilistic argument, so not a proof, but a heuristic for why there should be few or no solutions. And that heuristic actually also depends on these degrees, 2, 3, 7. And so somehow in that heuristic, the larger this quantity is, the less true you would expect the heuristic to be. So it's some kind of moral reason, the reason that for 237 and 238, there are a few sporadic solutions is because this quantity is so large. Now, it turns out there's no way to turn that into a proof. Why 1 over 42? It's just how that works. If you increase these, this ratio gets more negative, and this is just there's going to be some cutoff, and the cutoff happens to be minus 1 over 42. It could have been 333 or something like that, but so there's other modifications of Fermat's last theorem. A good one is to make these exponents equal and let this one be a square. In this case, when n is 3 or 4, this equation will have infinitely many solutions. But when n is at least 4, the only solutions to this equation are x, y, z is 0. So this quantity chi, okay, just do it. So it's 1 over n, 1 over n a half. So you get 2 over n, it's here, minus 1/2, that's this part. And this is strictly less than 0 if n is greater than 4. Okay, so when n is greater than 4, you do a short computation. And the Darmon-Granville theorem tells you, so same Darmon, that this fixed equation has finitely many solutions. What happened is, once Fermat had been proved and Darmon and Granville started looking at generalized Fermat equations, people really worked to push the methods in Weyl's proof to solve as many other families of equations as possible. So this was the first one. It's believable that it might be easiest simply because there's a 2 there. It really is the same techniques as Weyl's proof, but with some extra steps. So like 90% of the work was done in Weyl's original proof. And then for Darmon and Merel, they had to improve less the proof, but more the kind of inputs to the proof. So I'll give you a big slide in a minute. But the ideas used in Weyl's proof let you solve other. Oh yeah. So I'll come back to that question. Other. Oh yeah. So the previous question. So that's what the Darmon. So the Darmon-Granville theorem says there's only finitely many. And then in the same way that going from the Mordell conjecture to Weyl's proof goes from finitely many to none at all, they did the same thing Weyl's did. So they went that much harder extra step to show that these are the only solutions. So it doesn't follow from the previous thing. And then do we mostly just try? Oh yeah, okay, great. So yes and no. So here's great timing on that. Here's another question, but then you're just going to replace Fermat with something. Here's an ancient problem. So here's the Fibonacci sequence, and the ones highlighted in red, 118, 114, are the only perfect powers in the Fibonacci sequence. One's a perfect power, eight's a cube, 144 is 12 squared. And it was a conjecture for, again, like from hundreds of years, that these were the only perfect powers. This was only proved in 2006. So this is another Annals paper. It uses Weil's method, but it also needs a lot of other inputs. So there's something coming from transcendental number theory, this method of linear forms and logarithms, which they use. And I don't know, back to this question. I like doing number theory because there are such concrete problems that have connections to ancient mathematics. The problems are interesting, but also uh, if there's a really elementary way to solve it, it's actually not that interesting to me. Part of what's so interesting about this problem, I mean, part of it's the history and the simplicity of the statement, but part of it is that you need a battle crew, you need a starship to solve these. The techniques you use are incredible. The amount of machinery you need to prove a theorem like this is kind of outrageous and disproportional to the simplicity of the statement. And that doesn't appeal to everybody. But that appeals to me, the fact that these concrete problems have connections to so many other areas of mathematics. And about the PhD thing, I'll come back to that in a second. I used to run an RU at Emory, and so two of my students, Jessie Silliman and Isabel Vogt, my first RU student to get tenure, so she's at Brown now. You can kind of, in the spirit of your question, make up problems too. I mean, you can make up whatever problems you want. Some of them are interesting, some of them are not, some of them are too easy, some of them are impossible. So the RU project was take other Fibonacci-like sequences. The Fibonacci sequence is a linear recurrence relation. The next one is the sum of the previous two, but you could have some kind of more complicated or Fibonacci but different starting conditions. So you call these like the Lucas sequence. And this Lucas sequence actually gives you Mersenne numbers. So you can ask what are the only perfect powers in Mersenne numbers. And they kind of, or not kind of, they extensively studied this project and took these methods and pushed them as far as we were able to in 2013. So there are some Lucas sequences like Fibonacci where right off the bat, they can modify the method and it works. And of course, they're building on Weil's work. They don't have to recreate Weil's work from scratch to do this. Yeah. I think the answer is yes. Yeah. Or no. For squares, the answer is yes. But for perfect powers, the answer is conjectural yes, but we're not certain. So Jessie and Isabel were able to take the question about perfect powers in any linear recurrence relation and eventually get to some other question about elliptic curves, or rather abelian varieties, that's just independently interesting and has nothing to do with Fibonacci that we don't know the answer to. And so for some, yeah, this one follows from Catalan as well. By the way, sometimes there are infinitely many. So for 2, 3, 5, this quantity chi is positive. And so the converse is actually that, okay, there might accidentally be 0. Maybe there's a congruence condition, but once there's one solution, there's infinitely many. So this equation has infinitely many coprime solutions. And the exponents are not that large. It's 2, 3, and 5. For 2, 2, 2, these were Pythagorean triples, and it's not too bad to parameterize them. Actually, for 2, 2, 5, you can factor the left-hand side over the Gaussian integers. You need to use I and parameterize them that way. Here, the exponents are distinct. And yeah, thanks for bumping that question. The exponents are distinct, and it's actually an incredible amount of work to parameterize this. Here, let f be this. If you know modular curves, you might recognize this. These are the coordinates of the cusps on x of 5. So this polynomial comes from somewhere, but here it is. It's not too bad. It's degree 12. Let f be this. Let h be the Hessian. So this is the thing in multivariable calculus where you take the matrix of mixed partial derivatives, dx dy, dx dx, etc. So s and t, and its determinant. So that'll be a polynomial of degree, let me get this right, of degree 20. And then t is some other similar thing related to the dodecahedron, where you take a bunch of derivatives. And there's a formula for it, but I wanted to fit it on one line. And if you plug these three polynomials in, these are polynomials in S and T, you divide by some 2s and 3s to normalize them. And you plug them into this original equation, just somehow magically, these three gigantic messy polynomials, everything, when you multiply it out, exactly cancels and they solve. So then to produce a solution, you can plug in for s and t and that integers, and that will give you some solution. So why are there so many names attached to this? What happens is there's not just one f that does this. There's actually 27 different similar looking degree 12 f's, and uh, all of these f's, when you do this two-step procedure, give you polynomials which solve this. And then on the other hand, uh, where did it go? What Edwards proved is that every solution comes from one of these 27. The reason there are so many names attached to it is the first three people got it mostly right, but made some mistakes. And so it was actually an entire PhD student thesis by Edwards to fix those mistakes and give a complete proof. So yeah, the Hessian's related to the Jacobian. There's an extra derivative. It's the thing you do when you want to, like if you have a saddle or you want to understand min and max of multivariable functions, this is what you use. So why do we use the dodecahedron? Yeah, this is why Klein's attached to it. These polynomials don't come out of nowhere. Whatever this mystery exotic geometric object that this number is related to, uh, it turns out that geometric object is a sphere, and that sphere will have certain particular points. So this polynomial is kind of the coordinates of those points, and that those points, if you use those points, exactly correspond to the vertices of the dodecahedron. So you wouldn't guess dodecahedron, but when you look at the sphere, you would guess that there's this modular curve. There's some other geometric object that people already knew about, that Klein studied. It's actually, I'll even say it a little backwards. It's not that Klein studied this equation, it's that he was studying this other exotic geometric object and then realized this equation was related to it. And that other geometric object, even though it comes from number theory, the distinguished points on it give you the vertices of a dodecahedron. That's kind of where it comes from. Um, it's been a lot of progress. So here's just kind of a summary slide. We haven't solved the generalized Fermat equation yet, but there's a big list of work that was done after the proof of Fermat's last theorem. So Wiles and Taylor-Wiles, building on the work of a lot of other people, solved Fermat. I showed you Darmon and Morel. Another one, you can just see over time, lots of different authors get in on this. Back to the PhD question, Poon and Schaefer Stoll and then Bruin solved 2, 3n. The first three authors solved it for n is 7. That was my example from before. And so when I started my PhD thesis, after I passed my oral exams and everything, I read their 237 paper. The next prime after 7 is 11. And so I tried solving that. 11 didn't work. I mean, I did have a new idea, but I couldn't get it to work. And then much later realized that that same idea worked to solve 2, 3, 10. So my first theorem, my first publication, still published in a good journal, IMRN, but only 10 or 15 pages, was solving this one particular equation. And back to the question about producing problems and PhD students and stuff, this does make it seem like one thing you can do in number theory is some people worry it's a cottage industry is the word people use, is just keep trying to solve Fermat equations. The truth is, it's not just the Fermat equation that's interesting. It's really that if there's some Fermat equation, you look at the methods that are used, and for the new Fermat equation, there's some auxiliary question that's independently interesting that you have to solve. And so in these cases, there's some question about representation theory or Galois representations. And each line of this table doesn't just represent solving some Fermat equation. It represents some new progress in some other area. That then they kind of circle back and say, well, now that we answered this question, we can solve this Fermat equation. And then I didn't get to that yet. The curly ones work for every n, whereas the non-curly ones either only work for, yeah, here we go, only work for finitely many n or with some extra conditional thing. I'll put it that way. So there might be some condition on n that isn't on the slide that doesn't fit on one line. But the curly ones are comprehensive. Yeah. Maybe during the Q&A. So that's my hour. I didn't get to uniformity. This is usually where I stop this one. So I'll stop there, but I have a little bit of time to answer more questions after this. So thank you for your attention and for the great questions.
Yeah, thanks for a great talk. So, yeah, questions. Go ahead.
Yeah, let me circle back. There was one question. Has there been any work in number theory where you do exactly the same things and reestablish the same things, but with the operators modified? Oh, well, yeah, I mean, one thing I'm working on now is the Jacobi bound conjecture, but which is about differential equations, which seems pretty far away from number theory, except that, a differential equation is you have a derivative, you have axioms that derivatives satisfy. The actual conjecture is about the dimension of the space of solutions. So linear differential equations, if you take two derivatives, you get two parameters. It's two-dimensional. But there are, you ask about replacing operators, and this is something people do in the area of differential algebra. There are lots of things, I mean, formally you can do whatever you want. There are lots of things that look formally like differential operators. There's a Leibniz rule, there's a product rule, but they're not literally derivatives. Once you do that, you still get calculus and tangent bundles and stuff. And so ironically, the meeting I have at 2:30 is to meet with somebody to talk about that type of thing, replacing derivatives with other derivative-like operators and trying to generalize known conjectures to that. And you don't just do this for its own sake. I mean, it sometimes you do things for its own sake just to build up machinery, but usually when you build up machinery, like when you swap out operators for other operators, you're doing that because you have some application in mind. There's usually some balance between I have some problem, maybe it's not a Fermat equation, maybe it's not so concrete, but you have some other problem, and so you spend time building up machinery, but then that machinery becomes independently interesting. So anyway, that's all to say that, yeah, in about an hour, I'm going to go swap out operators and try to reprove theorems. Okay, so L functions. Yeah, the short answer is that L functions are a way to package together information at lots of different primes into one object that you can do calculus with. So for example, if I have some equation that I'm trying to solve, I can take and let me switch mediums real quick. There are lots of ways to do this. So you should see a whiteboard now. And it should be writing now. Let's see. There we go. Right. And so like if I have some thing that I'm trying to solve over finite fields, I can let NP be the number of solutions. So I'll say the size of X over that finite field. So whatever X is, that's some equations. This is the number of solutions to those equations over FP. And then you can package those together. Like if something has a lot of solutions over the rationals, you would expect it to also have a lot of solutions mod primes and maybe vice versa. And so what L functions do, I mean, this isn't what the L function is, but you could try to do something like take a variable mod NP and then take the infinite product of these. Okay, so this one, it turns out, is badly behaved, but what L functions are is it's a way to try to, so T is a variable, this is a function. It's a way to try to package information you have about your problem into some object that you can do calculus with. Okay, great. Curly. How far can Weil's proof be extended? Yeah, that's a great question. So basically to this slide, I'll put it that way. There's one remaining conjecture called the Frey-Maser conjecture that if you could solve it, you could solve all of the 2, 3p. But there's a really great paper by Darmon called Wiles plus epsilon, where he actually sets things up in the correct conceptual framework. What I mean there is at the beginning of Weyl's proof, there's this observation of Frey that if you have a Fermat solution, there's an interesting, weird elliptic curve you can write down, and then you quickly, depart from there and do stuff with those elliptic curves. And so Darmon actually found a conceptual way to classify completely the collection of exponents where Weyl's proof should work. And so the stuff on this table is more or less all of those exponents. Um, there is some hope. I've talked a little bit with John Voigt about instead of using elliptic curves, using higher dimensional things. Elliptic curves are one dimensional. And there's another larger, but still incomplete list of collections of exponents where we think that might work. But the exponents 3, 5, and 7 don't seem to fit into any of those frameworks. And 3, 5, and 7 are all primes, so there's no trick to reduce to a smaller case. And that's completely open. So even for exponents 3, 5, and 7, some fundamentally new idea independent of Weyl's work will be needed. So the ones on the screen, all in one way or another, the starting point, even this 51-page Punen-Schaeffer-Stoll, the starting point is Weyl's method. But then this will be a little vague. In Weyl's method, I mean, it's quite a lot of work, but at the end of the day, you get to a point where you start with your solution and you end up with some exotic Galois representation, but then Weyl's proves none of those can exist. What's difficult about the rest of these lines is, in some cases, when you get to the last step of Weyl's proof, um, like in this Punen-Schaeffer-Stoll, instead of none of these things can exist, they get to a point where they realize, oh, actually, there's 1,000 of these things that can exist, and we have to figure out how to rule them out. So there's kind of each of these represents some big extra step after Weyl's. Stacks, yeah, I love explaining stacks. Let me show you one stat. The actual definition of a stack is quite technical. But one of the things stacks do is the following. When I solve a homogeneous equation like this process of dividing by z to the n, so before I was saying x over z plus y over z is 1, right? So going back and forth, you can do this via group theory. And so if I take the set of solutions to this, and I take, let's just say the complex numbers, multiplicatively. So if I take some complex number, and if I take some solution x, y, z, and multiply by the complex number, if x, y, z were a solution, this is also a solution, right? Because lambda x to the n is lambda n to the x. Let me move that up, and so on. So what I'm trying to say here is to go from a surface to a curve, you quotient the set of solutions by c star. And what happens here is this is the easiest case of taking quotients. Nothing funny is happening. On the other hand, if I try to solve something like let me make my pen a little better. There we go. So something like x squared plus y cubed equals z to the 7. The same action doesn't work. So what I have to do is if I take x, y, z, I can twist the action. So I can have lambda act by 3 times 7. I can have it act on y by 2 times 7, and then act on z by 2 times 3. Sorry, so it should be lambda z. And so what I'm trying to capture in this formula, these are times, not minus, is that if x, y, z solved this equation, then and if lambda is any complex number, then this thing on the bottom also solves this equation. And so the difference is we had to add exponents into our scaling procedure. Maybe another way to put this is in the original Fermat equation, we only look at coprime solutions because if x, y, and z are all divisible by 7, you can just divide out by 7 to the n. That's what this action is doing. If these have a common factor, you can make it disappear. You can divide by it. Here, if 7 divides x, y, and z, that's not enough to be able to scale it down because maybe only 7 squared divides x squared, but 7 to the 7 divides this. So you have this more complicated formula. And so the motivation behind stacks is when you want to take the quotient, when you're trying to do the scaling, the the setup itself is messier. You have these annoying exponents, and so the quotient that you get is messier. So what a stack is it's a better way to take quotients. It's extra work, but it keeps track in a useful way of the fact that there are these exponents here. So that's really how they come up in this part of number theory. Stacks do a lot more than just that. Um, yeah, thank you. It's current work. It's kind of nebulous. I mean, so uh, right now that I'm a full professor, I just do whatever I want to do all the time. So I have a summer student, and we're trying to compute Ramsey numbers. That's not related to number theory at all. We have some new ideas, and probably won't work, but we're going to try it. My meeting later is using algebra and geometry to try to solve a problem about differential equations. Um, and then the thing I'm finishing up I'll tell you two more. The thing I'm finishing up that I met about yesterday is I didn't talk explicitly about modular forms, but whatever modular forms are, they're in the background of this. And then my collaborator and I have some new things we can say about modular forms, mod primes, and the relations between them, what they looked like when they lift to characteristic zero or not. Um, and then something more connected to number theory is when you solve equations like this, you can try to solve these over just the rational numbers, or maybe you want solutions over not just q, but q adjoin I or q adjoin square root of 2. Um, and I really like these questions of don't just solve the equation over one field, try to solve it over all fields at the same time. And so I've done a lot of work in the one-dimensional case, working on curves and looking at, you call these higher degree solutions. And so the most recent paper I finished is one of the first papers really looking at higher degree points on surfaces rather than curves. And just as an example, I showed you earlier that an equation like y squared equals, I'll just say x to the 6 plus 1. This equation has finitely many rational solutions. That's Mordell's conjecture. But it has infinitely many quadratic solutions because if I pick any rational number, right, I can let y be the square root of x squared or x to the 6 plus 1. This is not a rational number, but it is defined over some quadratic field. So as I vary x over rational numbers, I get lots of solutions to this equation over quadratics. The quadratic changes as x changes, but there are infinitely many quadratic solutions. And somehow what's happening here is, geometrically, this y squared is what's controlling it. What's really happening is uh, there's a 2-to-1 map, if I call this h, there's a 2-to-1 map from H to just the line. I'll be vague about what that is, but where I send x, y to x. And if I don't have the equation, but I have like a 4-to-1 map, the same thing works. If I pick a rational x, I'll get a quartic y. So the thing I most recently finished up is for curves, it turns out that there's like a rich historical theory of understanding I'll just say the two-ness of this, the fact that there's finitely many rational but infinitely many quadratic. There's something geometric, which is what's the smallest degree map from this to a line? And these problems even for simple surfaces were unknown. So I went to a workshop 2 Aprils ago where the goal was to just lay all of the foundational work, like answer the simplest questions we can about this higher degree question, but for surfaces. And so the paper we finished up was about 15 or 20 pages, took a simple class of surfaces called Delpezov surfaces that just a lot's known about them. They're easy to study, and just answered this type of question: when are there infinitely many quadratic or cubic for those? So kind of the first step in a new program of research. And then I will say, I, I do have some ideas about 357, the first unknown case. We're going to try. I mean, most ideas don't work out. You have to, 1 out of 10 things, if you're lucky, works out. So you just have to keep trying things. So technically, I'm working on that, but uh, nothing's worked out yet. So I do still think about this. So advice for high school math students. Yeah, read a lot is the advice. So um, and these books I mentioned earlier. I mean, you all know more than average, but uh, it's difficult to explain just how much or to convey just how much mathematics is out there. And so reading some of these popular math books like this is helpful. The truth is, you have to do two things very well. You have to learn foundations very well. You have to be able to do proofs and solve problems. Um, but to later on to have ideas, ideas have to come from somewhere, and ideas often don't come from learning the technical foundational material from 50 years ago. You still have to learn that, but you need to learn lots of other things. And so really my advice is, uh, well, two things. One is, learn foundations, but also just try to learn a lot of math. Just find interesting things and learn them. The other advice is there's no speed limit. Once you know how to do proofs and how to read math, you can just pick up books and read them. And once I realized that, like I still went to classes and learned the things that were happening in classes, but even as an undergraduate, I realized you can just go to the math library and pick up books, and some of them you can read and them you can't. Some of them maybe you can read the introduction and learn something, but the details are too much, but just like keep reading and learning things. And I mean, in a way that's vague advice, but really there's no speed limit. Once you know how to do things, you can just go learn whatever you want. Um, why are modular forms so helpful? So what people don't tell you is that whatever a differential is a thing that you can integrate. It's the thing, when you're actually working with manifolds and geometry, differentials or differential forms are just the things you can integrate. And you can figure out how to formalize that. Um, and modular forms are just differentials on very special modular curves. That's why they're so helpful. It's really the modular curves that are the things that are helpful, and the modular forms are just something attached to them. Um, of course, that's not the easy to state definition. The way most books work is they'll just tell you, here's the definition of a modular form. That's already enough work, but they won't tell you all the historical context or the 5 different ways to think about them. And some people, like Ramanujan, as far as I know, really didn't think about modular forms as differentials. Really, we're thinking about them as their Q series expansions. But the reason they're so useful is they connect to so many different things. But of course, that just punts the question: why are modular curves so useful? Right? Okay, well, they have large automorphism groups, and things which have large automorphism groups tend to give you representations, and so connect to representation theory. And yeah, and so like you can keep punting there. But it is mysterious, and I didn't get that until graduate. I didn't really internalize that until graduate school. Put it that way. What else? Did I answer everything? Yeah, part of what's fun about math and especially about working in arithmetic geometry is that I kind of get to do everything. Um, you have to learn geometry very well. You have to learn number theory very well. You have to learn representation theory very well. Some analysis. Uh, that's a pro for some people. That's a con for others as well. I really like being rewarded for learning difficult things very well. But the downside of this is you have to learn foundations very well, and that takes a lot of time. If you have a lot of time, then that works out well. There's also appeal to combinatorics where you can pick up a problem and just start working on it. And I like combinatorics too, but what I really like is projects and problems that take 2 or 3 or 5 years where I have to learn something well and deeply and then combine different, very technical things. So, and maybe this talk gives a little bit of that. So what I didn't get to and won't have time to explain is there are connections to, I didn't say what uniformity was, but there are connections to doing analysis on fractals, and these help you solve number theory problems. So these are what are called Berkovich spaces. If you know about p-adics, uh, an underappreciated fact is that the three-adic integers Z3 as a topological space are actually a fractal of the Sierpinski triangle. A three-adic is kind of, infinitely many 0, 1s, or 2s, but that's a recipe to tell you, zeros go north, 1 is go right, 2 is go left, and a three-adic number is a recipe to land you somewhere in this triangle. And so learning how to do analysis, yeah, helps. It's a connection between number theory and differential equations. Yeah, so there's two answers to that. One is you can do differential equations in the p-adic setting. And what's kind of neat, let me switch back to here, is that, nope, I don't want that. So two things, when you're working with series, let me make this more legible. When you're working with series, you know that if this converges, this implies that the ANs go to 0. But if these are in the p-adics, the converse is true. So this isn't differential equations, but when you're doing analysis, well, p-adic analysis is really easy because this converse is true. You can check convergence by just checking that the terms go to 0. Calculus would be a lot easier that way. There's no harmonic series. And there's a lot of crazy things, which is when you're working p-adically, again, if I have the sum of an over, I don't know, bn, when you're working in calculus, the larger the denominator is, the smaller this is. So large denominators make things converge. Whereas in p-adic analysis, what's happening is having powers of p in the denominator make things bigger, not smaller. And so what happens is something like 1 over n factorial, or maybe x to the n over n factorial, this is e to the x. This converges everywhere in real analysis, but in p-adic analysis, these denominators are bad. So there's this kind of thing that's swapped where everything that was easy in analysis is harder p-adically, and everything that was hard is easy. This doesn't converge everywhere p-adically. But this is a solution to a differential equation. Yeah, this is a solution to a differential equation. In general, you have functions p-adically, and you want to analytically continue them, meaning you have a formula for a function, that the formula only works, say, over here, but you want to know, and maybe you have a different formula for the same function over here, different expressions of it, and you want to connect those. One way to do this is to write your, like e to the x, write your function as the solution of some, in this case, p-adic differential equation, and then it's easier to analytically continue. So, I mean, so there's a lot of stuff that's vague there, but the point is the same things you do with functions, and that's what differential equations are about. There are functions in number theory in p-adic settings, and so differential equations give you another tool for thinking about those functions. And then the other answer is, which I didn't get to in the talk, is you can really go very far with analysis. And so these kind of fractal-like pictures, you can do analysis, solve differential equations. You can even do harmonic analysis, whatever that is. There's an analog of that there, except that these spaces also kind of have some combinatorics to them. There's a graph embedded in here that you can kind of see that the fractal kind of coalesces around. And so the neat thing about p-adics is there's a combination of analysis and combinatorics. Is there a concept of exactness enclosed? Yeah, exactness enclosed with modular forms like exact forms. Yeah, exactly. It's just that modular forms are forms on curves, so they're automatically closed. When you can, there are lots of different analogs of modular curves, modular forms, but on, like, there's a notion of a Hilbert modular form that's on a surface and not a curve. Then there's a question of whether it's closed or not. But on curve, that's one reason curves are easier, is forms are automatically closed. Yeah, why do we care about Fermat equations? By induction. I mean, that's slightly facetious, but there's a lot of things in math that I care about this because I already care about this, and I care about this because I already care about this. That's not a great answer, though. I don't know why we care. I mean, I care about Fermat equations because the statement of the problem is so simple. There are lots of special cases that make you start to think, the cases you can do by hand in an elementary way, like when n is 3, that's a medium difficulty problem, like elementary number theory problem that you could conceivably do on your own now, just with bare hands. And you start to think that, oh, maybe this elementary problem isn't very hard, but it turns out to be pretty hard. And what's really interesting about Fermat's last theorem for me is just it's more about how hard the problem is. Like if you just looked mod 5 and there were no solutions, it wouldn't be a very interesting problem. The fact that what's so interesting about it is how much machinery it takes. Um, yeah, yeah. And so you can do calculus on spaces like this. There's a bunch of different variations of calculus on fractals, and you can do calculus and harmonic analysis and differential equations, Yeah. And there's a good reference. So these slides are available online, but the Baker, Payne, Rabinoff is good keywords for that. Um, yeah. Do we know if what is undecidable? Yeah, I mean, yeah, the Riemann hypothesis might be undecidable as well. Like maybe the other remaining clay problems are all undecidable. We don't know for sure either way. Um, maybe time for one more before.
Well, okay. So if there are no more questions, thank you again for a great talk and an engaging session. So let's now move on to the next stage of class.